Imagine plugging directly into your car's wiring harness and pulling live data, like engine RPM, vehicle speed, and coolant temperature, straight from the onboard computers to a custom dashboard. Before you can read that advanced telemetry, you need a way to interface with the network. Today, we will build a foundational two-node physical network from scratch using the ESP32 microcontroller. To follow along, you will need two ESP32 boards, two TJA1050 CAN transceiver modules, and some twisted pair jumper wires. Mastering this tabletop setup provides the technical foundation for building custom web-hosted telemetry dashboards. Early vehicles relied on point-to-point wiring, where every single switch and sensor required its own dedicated cable, resulting in massive tangled harnesses. The Controller Area Network, or CAN bus, solved this by acting as a central nervous system. Instead of individual wires, electronic control units broadcast their sensor data over a shared bus, making it available for any other module to read simultaneously. When idle, both bus wires sit at 2.5 volts, the recessive state. To transmit a logic 0, a node drives the high line to 3.5 volts and drops the low to 1.5. creating a 2-volt differential called the dominant state. These bits are packaged into a standard CAN frame with 8 specific fields. The most important parts are the 11-bit identifier dictating message priority and the 8-byte data payload holding the actual sensor values. Knowing how voltage shifts create structured frames is necessary to correctly configure our microcontroller's internal settings. The ESP32 actually has a built-in CAN controller, but Espressive refers to it as the TWAI, or Two-Wire Automotive Interface. For our purposes, TWAI and CAN are identical. The TWAI controller supports 3 modes. First is normal mode, second, no ACK mode, and listen-only mode. Listen-only mode is crucial, allowing the controller to passively read data without transmitting, keeping live vehicle networks perfectly safe. While the ESP32 can handle logical frame processing, its pins cannot physically generate the 2-volt differential required for the dominant state on the bus. That is why we must use an external component like the TJA1050 transceiver. It sits between the microcontroller and the network to translate low-voltage logic into automotive-grade physical signals. Let's set up the hardware. Place your 2 ESP32s and 2 transceivers onto 2 distinct breadboards. On the first board, connect the transceiver's VCC to VIN and ground to ground. Next, link the TX pin to GPIO5 and the RX pin to GPIO4 to establish the logic connection. Repeat those exact connections for the second node. Then, physically connect them by running twisted wires between the boards, wire CAN high to CAN high and CAN low to CAN low. In a high-speed data bus, signal reflections can bounce back and corrupt the communication if the line is left open. To prevent this, the far ends require 120-ohm terminating resistors, which the TJA1050 modules have pre-installed. With logic pins wired, boards linked, and the line terminated, our physical layer is complete. To drive the TWAI controller, we need the right software library. Open your Arduino IDE and navigate to the Library Manager. Search for the term MCP2515 and install the library specifically titled CAN, authored by Sandeep Mistry. Copy the transmitter code from the documentation and upload that sketch to your first board. This code instructs the board to act as the sender, broadcasting a standard 11-bit CAN packet onto the wire exactly once every second. Next, copy the receiver code and flash it to the second ESP32. This second board is now passively listening to the physical bus. Upon detecting a valid frame, it decodes the payload and prepares to print the result. To view that payload, open your serial monitor. Make sure you set the baud rate to 115200 so the incoming data renders clearly instead of appearing as unreadable characters. Once connected, you will see a continuous stream of Hello World packets populating the screen. You just created digital logic in code, converted it into physical 2-volt differentials across a wire, and decoded it perfectly on the receiving end. Now that you have a functioning tabletop network, you can switch your configuration to listen-only mode, connect this exact hardware to your vehicle's OBD2 port, and start building your own live telemetry dashboards.